There is a place in the ocean where water forms lakes.
Water. We're going to stick our finger in it just to see.
We can do that.
And we should see, we might even see little ripples on it, and you might see kind of layering water as it tries to mix. So we'll go to a brine pool next week. Yeah, you can see the
shimmer.
The shimmer around the arm.
Wow.
For the first 5
More
days.
oil.
I'm going to get off in the 10th.
Yes.
Not ice, not land. Liquid lakes thousands of meters below the surface. They have shorelines, they have waves, and if a fish swims into one, it doesn't struggle, it doesn't escape. It simply stops. So how can a lake exist inside the ocean itself? In the past few years, deep-sea exploration vehicles in the Red Sea have noticed something unusual. Areas where no living thing exists, no oxygen, no movement. However, the chemistry in these areas indicates that something else is at play, something active, something living. And over the next 22 minutes, we will go deeper than the sunlight has ever penetrated to reveal the truth about these underwater lakes and why they may be one of the most significant discoveries in oceanography. Because the real mystery isn't what dies in these lakes, it's what lives inside them. If you're not afraid, subscribe and take a breath, and let's go deeper. To understand how a lake can exist inside the ocean, we have to forget how we think water behaves. Because these lakes are not held in place by land. They are held in place by weight. Millions of years ago, this part of the seafloor was buried beneath thick layers of salt. As tectonic plates shifted, that salt was squeezed upward, slowly dissolving into the surrounding water. What formed was brine, not ordinary seawater, but water so saturated with salt that it became heavier than anything above it. This density is the key. Normal seawater floats on top. The brine sinks and stays locked in place, unable to mix. That's why the boundary looks so sharp. It isn't a shoreline made of rock, it's a chemical wall. But salt alone isn't what makes these pools deadly. As the brine seeps through ancient sediments, it absorbs methane and hydrogen sulfide, gases released from deep within the earth. Together, they strip oxygen from the water entirely. No oxygen means no breathing, no metabolism, no escape. The moment an animal crosses the boundary, its nervous system shuts down. And yet, the ocean above these pools is full of life. Fish swim freely just centimeters away from a place that would kill them instantly, which raises a disturbing realization. These lakes are not rare accidents. They are stable, persistent, and likely far more common than we once believed. Some have remained unchanged for thousands of years. Silent, invisible, waiting. But chemistry alone doesn't explain the strangest part, because if these lakes are truly uninhabitable, why did scientists detect biological activity inside them? Because what they found next forced researchers to rethink what toxic really means. The most disturbing part of these underwater lakes is not what they are, it's the edge. A sharp, invisible boundary where normal seawater ends, and something far heavier begins. When remotely operated vehicles hovered above these pools, the cameras revealed a strange behavior. Fish would approach the surface, slow down, and hesitate. Some turned away at the last second, others crossed it. And the moment they did, everything changed. Their movement stopped almost instantly. No violent struggle. No frantic escape. Their bodies stiffened as if a switch had been flipped. This wasn't drowning. The brine contains no oxygen, but the effect happens too fast for suffocation. What occurs is neurological. Extreme salinity, combined with toxic gases, overwhelms the nervous system, shutting down muscle control within seconds. Crabs froze mid-step. Fish drifted, motionless, then settled gently at the surface below. And that's when scientists noticed something that didn't make sense. The bodies didn't decay. Normally, when an animal dies on the seafloor, the process is quick. Bacteria move in, scavengers follow, soft tissue disappears, and bones are scattered by currents. But at the edge of these brine pools, none of that happens. The chemistry is too extreme. There is no oxygen. The salinity is overwhelming. The gases dissolved in the brine are toxic to nearly all known life. The microbes responsible for decay cannot survive here. As a result, the bodies remain. Fish lie where they fell. Crabs stay frozen in the positions they died. Skeletons slowly accumulate along the boundary, tracing the outline of the lake itself. This is why scientists often describe brine pools as natural archives. Every mistake is recorded. Every crossing leaves evidence. The chemistry does not dilute. Time simply passes around it. Life continues just centimeters away, completely unaware, which leads to an unsettling realization. These lakes are not chaotic. They are stable. And if the boundary is this precise, this selective, then the real mystery isn't why animals die here. It's why anything at all might survive beyond it. For a long time, scientists believed these brine pools were completely sterile, too salty, too toxic, too hostile for anything to survive. By every known biological rule, life should end at the boundary. But when researchers began sampling the brine itself, the data didn't match the assumption. Chemical sensors detected activity. Not movement, not large organisms, but metabolism. Inside the brine, where oxygen is absent and toxins dominate, microscopic life was thriving. These were extremophile bacteria, organisms adapted to conditions that would instantly kill most life on Earth. Instead of oxygen, they use chemical reactions to survive. They metabolize methane, they process hydrogen sulfide, they draw energy directly from the chemistry of the brine. In other words, what makes these lakes deadly to fish is exactly what makes them habitable to something else. This discovery forced scientists to rethink the definition of a dead zone, because these lakes were not empty. They were ecosystems, completely isolated, chemically driven, and invisible from above. Which raises a much larger question. If life can exist here, in conditions this extreme, what does that say about where life might exist elsewhere? These extremophile bacteria do not need sunlight. They do not rely on plants or oxygen or the food chains we recognize. Their entire ecosystem is built on chemistry. Energy flows not from the surface, but from the Earth itself. This makes brine pools something rare in biology. They are self-contained worlds. No fish enter, no predators hunt. No currents mix the water. Everything that lives here is adapted to isolation. And that isolation matters, because these bacteria do not just survive, they alter their environment. Over time, they influence mineral deposits, chemical gradients, and even the structure of the lake itself. The brine pool becomes stable not just because of physics, but because life inside it reinforces the balance. This realization changed how scientists viewed these places. They were no longer just hazards on the seafloor. They were laboratories, natural experiments running for thousands of years. And that opened a much larger line of thinking. If life can exist without sunlight, without oxygen, and without contact with the surface, then oceans like this no longer feel unique. They begin to look familiar. Because elsewhere in the universe, there are worlds covered entirely by dark oceans, and the conditions inside these brine pools may be the closest analog we have to what exists beneath their ice. For decades, scientists believed life required three things: sunlight, oxygen, and constant exchange with the surface world. Brine pools broke all three assumptions. Here was life with no light, no oxygen, and no connection to the ecosystems above. That realization changed more than marine biology. It changed astrobiology. Because when scientists looked at these lakes, they didn't just see a deep-sea anomaly, they saw a model for how life might exist elsewhere. On moons like Europa and Enceladus, thick ice covers vast global oceans. No sunlight reaches those waters. No atmosphere mixes with them. No surface ecosystem feeds them. And yet, chemical energy exists. Heat from planetary cores. Hydrothermal reactions. Subsurface chemistry, the same forces that sustain life inside brine pools on Earth. This is why brine pools became a focal point for space agencies. They offered proof that life does not need familiar conditions. It only needs stability, energy, and time. And Earth's deepest oceans provided all three, which led scientists to an unsettling possibility. If life can exist here, isolated and unseen for thousands of years, then the universe may be far more biologically active than we ever imagined. Brine pools didn't just change where scientists looked for life, they changed how they looked. Instead of searching for large organisms or familiar ecosystems, researchers began focusing on chemistry, energy gradients, reaction pathways, places where matter is forced to adapt. Because life, at its core, is not about comfort, it is about persistence. Inside brine pools, bacteria survive by exploiting tiny imbalances. A difference in salinity, a trace of methane, a slow seep of chemicals from the seafloor. That same logic now guides the search beyond Earth. Space missions no longer ask, "Is this place like Earth?" They ask, "Is there energy here? Is it stable? Has it been this way long enough?" Brine pools prove that isolation is not a barrier to life. In some cases, it may even protect it, shield it from predators. Undisturbed by surface catastrophes, locked in conditions that barely change over time, which leads to a quiet but powerful conclusion. If life can hide here, in the darkest parts of our own ocean, then the universe may be filled with biospheres that have never seen a star. Not rare, not fragile, just waiting beneath the surface, following rules we are only beginning to understand. Brine pools are not just a strange feature of the seafloor. They represent a turning point. For centuries, humans believed the deep ocean was lifeless. Too dark, too cold, too extreme. Then we discovered life. Then we discovered ecosystems. And now, places where life and death exist side by side, separated by nothing more than a chemical boundary. Brine pools force us to confront a deeper truth. The limits we place on life are human assumptions. Nature does not follow them. Life does not require comfort. It does not require light. It does not require stability as we define it. It only requires a way to persist. In these lakes, chemistry replaces sunlight. Isolation replaces interaction, and survival takes a form we would never recognize without technology. This is why brine pools matter beyond biology. They reshape how we think about habitability. They redefine what an ecosystem can be. And they remind us that vast portions of our own planet remain unexplored. Because if something this alien exists on Earth, hidden in plain sight beneath kilometers of water, then the unknown is not rare, it is normal. For most of human history, the ocean felt empty, too vast to understand, too deep to explore. Brine pools changed that perspective. They revealed that even in the most hostile environments, life does not retreat. It adapts, not by becoming stronger, but by becoming different. These underwater lakes exist quietly, untouched by storms, seasons, or sunlight. They persist while the surface world changes above them. Extinctions come and go. Climate shifts, oceans warm and cool, and still these systems remain. That permanence carries a lesson. The most resilient forms of life are often the ones we never see. They do not dominate. They do not spread. They endure, As we continue to explore the deep brine pools, remind us that Earth is not a solved world. It is layered, compartmentalized, full of environments operating by rules we are only beginning to understand. Somewhere below the waves, entire ecosystems exist without our awareness, not hidden by secrecy, but by depth. And if places like this can exist beneath our own oceans, then the universe may be far less empty than it appears, not filled with familiar life, but with life that learned how to survive where nothing else could. Death in the deep ocean is usually temporary. When a creature dies, the seafloor responds almost immediately. Bacteria begin breaking tissue down. Scavengers emerge from the darkness. Currents scatter what remains. In most places, nothing stays intact for long. But brine pools interrupt that process completely. At their edges, decay slows and then stops. The same chemistry that makes these lakes deadly also prevents decomposition. There is no oxygen to support decay. The extreme salinity damages cell membranes. Toxic gases disrupt the chemical reactions that normally break organic matter apart. As a result, bodies do not rot. They remain exactly where they fell. Fish lie motionless at the boundary. Crabs stay frozen mid-step. Skeletons accumulate in place, outlining the shape of the lake like a shoreline made of bone. This is not fossilization. It happens far too quickly. And it is not freezing. The water temperature is not low enough to explain it. What occurs here is chemical preservation, a process capable of halting biological time almost instantly. In some cases, animals recovered from brine pool edges showed tissue preserved far beyond what should be possible at these depths. Muscle structure remained intact. Internal features were still recognizable. For scientists, this was unexpected. Brine pools were no longer just dangerous environments. They were natural archives, places where death is recorded instead of erased. Each preserved organism becomes a snapshot, a moment captured at the instant chemistry took over, and that raised a new possibility. If brine pools can preserve life this precisely, what else might they be preserving? This preservation gives brine pools a rare scientific value. In most deep-sea environments, researchers arrive too late. By the time a vehicle reaches the seafloor, the evidence is gone. Soft tissue has vanished. Only scattered bones remain. But at brine pool boundaries, the story is still intact. Scientists can observe how animals died, where they fell, and what crossed the boundary moments before death. They can study muscle structure, organ placement, and chemical damage that would normally disappear within hours. In this way, brine pools act less like graveyards and more like records. They preserve biological moments that would otherwise be lost to time. This has allowed researchers to better understand deep-sea species that are rarely seen alive. Creatures that live in darkness, pressure, and isolation can be examined without the distortion caused by rapid decay. In some cases, brine pools have revealed species interactions that were never documented before. Predators frozen beside prey, scavengers caught mid-approach. These scenes offer insights not just into death, but into how life behaves at the extreme edges of survival. What makes this even more remarkable is that this preservation is selective. Only the boundary holds these records. Just centimeters away, the normal ocean erases everything. That sharp contrast highlights how narrow the line between existence and disappearance can be in the deep sea. Brine pools do not preserve life forever. Over time, chemistry still wins, but they slow the process enough to give science something rare, a chance to observe life as it truly existed, not as fragments reconstructed after the fact. In the darkest parts of the ocean, where nothing is supposed to last, these underwater lakes quietly hold on to the past. Not out of purpose, not out of design, but because chemistry, under the right conditions, can remember what biology cannot. Despite covering more than 70% of Earth's surface, the deep ocean remains one of the least explored environments on the planet. We have mapped the surface of Mars in greater detail than the seafloor beneath our own ships. That is not because the technology does not exist. It is because the ocean actively resists observation. Pressure increases faster than almost any machine can tolerate. Darkness absorbs light within minutes of descent. Salt corrodes metal. Currents shift unpredictably, and communication becomes unreliable the deeper we go. Every additional meter multiplies the difficulty. Brine pools are a perfect example of this limitation. They were not discovered because scientists were searching for underwater lakes. They were found by accident. A camera drifted lower than expected. A sensor detected something heavier than seawater. An ROV crossed a boundary that instruments could not explain. And suddenly, an environment that may have existed for thousands of years entered human awareness for the first time. That moment revealed an uncomfortable reality. If a feature this extreme, this deadly, and this distinct could remain hidden for so long, how much of the ocean do we still misunderstand? Vast regions of the seafloor have never been seen directly. Entire mountain ranges are known only through sonar shadows. Chemical systems are inferred from data, not observed with human eyes. Each expedition uncovers something unexpected, not because the ocean is changing, but because our understanding is incomplete. Brine pools did not suddenly appear. They were always there. We simply lacked the perspective to recognize them. And that suggests the most important discoveries in the ocean may not be dramatic events waiting to happen, but quiet systems waiting to be noticed. What brine pools ultimately reveal is not just how extreme the ocean can be, but how incomplete our picture of it still is. These environments were not hidden by distance, they were hidden by assumption. For a long time, scientists believed the deep sea floor followed simple rules. Water mixed. Life faded with depth. Chemistry became uniform. Brine pools shattered that idea. They showed that the ocean is layered, compartmentalized, and capable of creating isolated worlds within itself, places where chemistry overrides biology, where boundaries exist without walls, where life and death are separated by a line thinner than a meter. This realization changes how we approach exploration. It suggests that the unknown is not confined to the edges of maps, but embedded within environments we thought we understood. As technology improves, each descent reveals systems that were never predicted. Not anomalies, but consequences of physics, chemistry, and time interacting in silence. Brine pools remind us that discovery does not always come from searching farther. Sometimes it comes from looking differently, from questioning assumptions, from noticing what does not behave as expected. Beneath the surface of our own planet, entire ecosystems operate without our awareness, shaped by forces that do not announce themselves. The deep ocean is not empty, it is not uniform. It is a world still revealing itself slowly, layer by layer, boundary by boundary. And if places like these can exist beneath our oceans, undetected for centuries, then the greatest discoveries ahead may not be waiting in space, but still resting quietly below the waves.